Okay, so is everybody kind of getting the same behavior in their model? Then let's actually I'm interested to see. I'm gonna go back to the profile and let's kind of scroll through the J's and kind of get a sense of so getting back here to all these little gotchas. There we go. So what I was interested in looking at the end times and kind of scrolling through the layers and the J. Go backwards. Interesting, yeah. So this is the most inner cell or column, or excuse me, row of cells around the bend. So we're getting an initial scour at the front side, and then kind of little to no either erosion or deposition occurring just before it exits, and then we get this kind of depositing section right here. And that is that one. So let's look at the KD equal to 1,000 test case. Same process. Look at the slice. Should look absolutely identical at the initial conditions. But now we will turn on the animation and kind of see how this model behaves. Everybody's when you first bring up the plot after you've reloaded the model, all the settings are still saved. It didn't. It probably actually should just reset them, and you'd have to manually load the setup file. But most things, if you load a new model, most settings are reset. But some of these graphic settings may not necessarily be automatically reset when you load a new model. So that's something to, if you're loading quite diverse models from model to model, you'd probably want it reset. But if you're loading the same typical model and just looking at different scenarios, it's kind of nice that it doesn't change. But anyways, that's the reason why all your settings are okay on this one. So we'll just animate this. Did I turn off diffusion in this one? It doesn't look like it. Did I save it? Got KDs. I still left on all this. That's the problem. I'm trying to eliminate, doesn't really matter what I put here, but trying to eliminate the dissolve phase flow. Now that should mine hopefully make it look a little bit more like I'm expecting. Because I had forgotten to turn off pore water diffusion. And what I want to do is actually kind of look at varying volatilization. Let's look at a few processes that we can adjust for volatilization and see what impact it has on the results. We need to run a mass balance on this so we can show how much mass is being lost, because we should be getting it actually in grams of toxic loss due to the volatilization. And if we were running, actually if we were running double precision, of course it'd be even more exact on 0. And maybe if we're going to look at mass balance, I should just give you guys the double precision executable. And we'll use that instead. In fact, I'll just do that right now. It runs a little slower. I mean, that's the thing about the double precision. That's the reason why we just don't straight up use it by default, because when you accessing, it's bigger. I mean, the arrays are all double in size in memory, so it just slows down just a little bit. All its lookups and everything, you know, it's about 10% slower than a equivalent single precision model. It's kind of what we have experienced. So do we have to put that on the, well, I guess I'm not on the internet, so yes, we will have to put it on your machine, whatever. Let's try that again, see if it'll work. Maybe it'll work this time. Still compiling. Oh, that's right. Mouse doesn't work when that's plugged in. Yeah, let's see what this looks like. 8, view, animate. Yep, that's behaving more as expected. Still see, as I was saying, you know, you'll still see a little bit of the you know, kind of deviation away from one right at the active layer where there's so thin sediments that it kind of varies a little bit. But, you know, any kind of more typical layer thickness where, you know, it basically just kind of hangs right at 1 milligram per kilogram. And you don't see any significant, you know, higher concentrations in this. See, this is the depositional zone, and remember we have bed load turned on, and if we don't remove that material coming down the flume due to bed load and move it to the downstream cell, we would be getting a significant accumulation of sediment in that cell there. So not only from a mass perspective on the sediments, but also a mass perspective on the toxics. You know, it's behaving pretty much as expected. So, you know, this was our kind of final test, other than mass balance, to make sure that we maintain mass balance. But this test here kind of demonstrated that the processes of moving the toxics around with all the individual pieces, because there's a lot of sediment moving between layers and bed load and suspended load and deposition, that all those are all being tracked properly. And so we bless this. You're done. Although it's not quite done. There's always something that needs to be else to happen. So let's see if actually this double precision, let's run it in double precision and we'll just show you the difference. And again, I don't think it's necessary the majority of time. Come on, mouse. There we go. Yep, there we go. Yeah, it's just too small to work with. I'm going to give you guys the double precision. Let's run it in the double precision. So let's look at mass balance. And you do that again through the model analysis tab, and then miscellaneous tab on the top, and then the mass balance tool here. I'll show you what happens. This is just an artifact of snapshot frequency, but let me show you what happens with the water. So this is the volumetric balance for the model. 0.5%. So that doesn't sound all that good from a mass balance perspective. Two things are going on. Number one, this is single precision. Number two, the reason why the relative percentage is so high is because my initial volume is so infinitesimally small compared to the amount of water that came in. But more importantly, it turns out it's actually because my 1 minute snapshot frequency output doesn't exactly correspond to my boundary condition. And since I have this really sharp boundary condition, to improve mass balance, you either increase the frequency of your snapshot or here. Or I adjust this peak so that the peak is right at one of my snapshot increments. Because right now what happens is I get a snapshot. You could say I get a snapshot here, and then I get a snapshot here, and I miss the peak. And so my mass balance is a little off, and I know that because I have a run where I tested. I just moved the peak to exactly correspond right on my snapshot frequency. So majority of time, things are much smoother in an environmental world. But still, if your snapshot frequency output is, say, hourly, you're going to miss some of these peaks and valleys. So again, the mass balance tool is more useful for just kind of getting a good understanding of general behavior of the model and where your masses are coming in and going, and you know, if you're close. But when you're running, you know, this particular test case, I want it to be near zero as far as mass balance error. So that's the reason why we were playing with that. But now that doesn't have an impact on your mass loadings, because this is all, you know, it's being computed from the actual boundary conditions and all the net accumulated material inside the model. So now when I go in here to model analysis, mass balance, and I go to cohesives, just view time series. See here, it's reading the snapshot data and actually, you know, calculating the mass balance. And we had this, and this is what we want to go away. So right now it's still a very, very small number, but this is based on single precision results. So we're going to run the same model with double precision and see what happens to that number right there. And to the, I'll show you what it looks like. If you turn off all the other series except for the error, then the automatic scaling over here shows you the kind of detail of what's going on, and that is what it looks like in single precision. So I'll just export that. Now, let's go ahead and run this model. You could run it and put it in a different folder. I guess let's just do that. Double precision. So I just copied that to the clipboard and saving this out. Now, to change executables, it's really easy. You just use that settings tool and just browse to the other executable. And as long as the executables are sitting in your installation folder. So everybody have the executable? We make available on our website by default the debug version of EFDC, current version, and the double precision version. So you can download it and use it if you want, but we just don't package it up with the main package. Again, it's available there for use.
So the release version is
Single precision.
Release version is what package.
That's right. But the double precision and everything works perfectly fine. You can just swap back and forth with no problem. Now, it's double precision, but it's not, what is it, I-64. It's still a 32-bit application. It's not a 64-bit application. It's just using double precision arrays. So your precision of your numbers are still really good, but you still have limits on executable size, and there are still some 32-bit operating system limits. We haven't really seen much of a need to go to 64-bit yet, but I'm sure we will. Eventually, we'll just end up, releasing the 64-bit version of it. But it really only affects things like file size. Well, I think we can already be like half a terabyte or 2 terabyte, whatever I think it's close to actually 2 terabyte file size with a 32-bit operating system. So if we're up to 32 terabytes on a file, we have other issues. Let's turn off volatilization and then run it. Ignore. Now, save it and run it. I have to select my double precision because I still have single here. So while we're doing that, let's look at the form here. Some other things I think it'd be useful to kind of do some sensitivity work with. And that's in the one of the places I think it's useful to do some sensitivity work with is in the diffusion rates, and kind of look at maybe an order of magnitude step and kind of see how diffusion is impacting our water column and sediment bed concentrations. So I actually want to, but I don't want to do it with the KD 1000. I want to jump back to a more realistic test case with the naphthalene. Yeah, but let's see, that by the time I get finished talking, the model will essentially be done. Not quite, 1/3 done. But that's what I want to do next, and I'd like to start with. I think right now we're using 10 to the minus 8, and then we'll try what if we do 10 to the minus 7, 10 to the minus 6, and kind of see how that drop affects the water column and the sediment bed. Let's look at the mass balance for the double precision without, make sure after all my talking that I actually did turn it off. I did. So everything's off. Kinetics are all off here, and then the high KDs and diffusion is turned off, and we should be good. Mass balance. Look at toxics. View the time series. Calculate. Now that's more like it. I mean, mass balance sediments, mass balance toxics, but if you really want this precise of a mass balance, you got to run double precision. The loss term, you know, you saw the amount of volatilization was a very small number. I don't know what the actual mass was, but you know, we were losing material through the atmosphere. Question. I would love to find a test case that we can validate I mean, I've got the code. I believe the theories, you know, the code is representing the theory. I'm confident of that. Now the question is can we take it to the next step and validate the volatilization to an actual either, you know, theoretical analytical calculation or an actual, you know, study where we know volatilization rate. I'd love to be able to do that demonstration step to make sure that we're reproducing. Because, I mean, there's really not a lot. If you look at the volatilization, I want to show you this actually. On the air term, when it is, you know, near mass balance. Now this is a systematic behavior. It is a very, very small number. But it's still, not that. I meant to turn that on. Keep that automatic. I mean, it's a, there is some systematic error here. I think this is, some of it's probably associated with what's going into the bed load. But then as the bed load concentration decreases, it's adding it back to the bed. But I account for it in the mass balance. So anyways, it's just something that I have seen the same behavior, but it's just extremely small numbers. So we were looking at volatilization. You look at, I mean, there is really not a lot of adjustment here to the volatilization rate. Other than, that's one reason why we added this multiplier here. If you just feel like the volatilization is too high, you can just arbitrarily, based on a calibration knob, crank it down right here. This is just a straight up knob. But the rest of this stuff, I mean, Henry's constant's a fairly well-established number. Obviously, molecular weight, well-established number. The temperature correction factor, you know, that could vary a little bit, but it's, you know, it's not going to probably be the dominant, you know, factor of what's affecting you, your system. And then, you know, obviously, you might have some small atmospheric concentration that could be influencing your result. But there's not a lot of tweakable parameters in that set of input data. So, I mean, it's either right or not kind of thing. And so I'd love to be able to test that. So anybody have some thoughts? Let me know, please. Yeah, so let's, what we want to do is actually play around with diffusion. So, well, I'm gonna start up with the naphthalene test case. Actually, what I had suggested is that we raise the diffusion rate, but frankly speaking, after looking at this profile, and seeing the higher concentration in the water column, I'm thinking that the diffusion rate's probably too high. Given this particular, oh yeah, it's still screwed up there, isn't it? It looks like I'm going to have to exit. Oh well, okay, well I'll do that, and then I'll restart. Schedule J talks. Always have to redo this stupid size thing.
You guys will receive a feedback form on your email sometime today or Monday. So we'll really appreciate it.
Let Janesh do all the training. That's my feedback. Okay. So what I was saying is that I was just looking at this and, looking at this profile here, and, I'm thinking that there is, seems to be a fair amount of pore water diffusion happening here, causing this this behavior. So I want to change that around a little bit by reducing instead of increasing the diffusion rate, I want to decrease the diffusion rate. So let's just see here, diffusion and mixing. So I'm at 2 times 10 to the minus 8. I'm just going to do 1 times 10 to the minus 9. So 5 times slower pore water diffusion at the, well, let's just do it that. Let's just try just that one and see the impact. Is the beauty of, that's what I'm supposed to do. And save this out as and run it. Is there anything, other things that would be of interest that you guys would like to look at? I think we should probably, well, let's just go ahead and start up another run while we're at it. I think I showed you guys, we talked about this, but I've got this model running, and in Windows 10, I'm using 2 cores, and this is the resource monitor, which is the same as the old task manager. But you can see that I've got, I turned on 2 cores, and so I've got these 2 cores being 100% utilized, or these 2 threads, which means that this core and this core, physical core, are being used. But down here, I still have available space. So I'm going to run the other run on those 2 cores. So I'm going to go in and change. This time, I'm going to also decrease the bed mixing by an order of magnitude. Save it out. This will all be very cryptic, which means tomorrow I won't remember what any of this stuff is, but that's okay. We do right now. And so I'll just run on the other 2 cores. So now when I look at the resource monitor, if I can get my mouse to behave, there we go. So this one's fully operational, and now you can see initially while it was actually just kind of doing the initialization, only 1 core is used. You don't actually use, oh, that model's finished. Okay, oh well. can't quite see it as nicely as I was hoping, but anyways, we should have seen 2 fully utilized cores here. So, with Eight threads, 4 cores. There's 2, it's a hyper-threaded system, so there's 2 threads per core, but essentially all they do, they're designed for user interface throughput because they're constantly swapping, but there's only one physical core doing computations. So it really doesn't pay to use both threads when you're using a heavy CPU application, because all they're doing is they're just swapping, and it just slows everything down. So that's why I lock them thread one thread per physical core. Okay, so this one's done. We'll look at first. We'll look at the mass balance. I'm going to turn on the time series. We'll look at the toxics. Now this I should have less loss than I had before because I've lowered the diffusion rate. I don't know how much it'll be, but it should be less. Actually, it went higher. Am I using double precision? Or, oh, I think I didn't. Well, maybe I did. I don't know. I don't know. Now I've got to run it to find out. I don't know if this is exactly the same run as we did with the other one. Turn off. Yeah. So that's the rate of volatilization loss in the system. I decreased my pore water. Let's look at the longitudinal profile and see what if that is behaving as expected. Which I should see things a little less tending toward blue in the sediment column. And that is, you can definitely see that you're still fairly significant. I wonder if the particle mixing is making that much of an impact. This is why I love having these little quick runs like this, these test cases, because you can gain a lot of insight into the model performance and behavior by just making these quick little runs on something that runs fast and is easy to visualize, and then you can take what you've learned and scale it up to your larger scale model. Just saves a lot of time when you're trying to run really big models, and you've got you're playing with a parameter, so you can just do it a lot quicker here. Now, obviously, it's not going to be one-to-one correlation, but you'll certainly get the sense of the behavior of the system. So let's just see what happens. We shut that thing down and leave pore water on. So if I just turn off my particle mixing, no mix, and run the model, and we'll see how that behaves. And while that's done, we can look back at this one now. So this one is ten to the minus 9 and 10 to the minus 9. So here that other one we were looking at still had the pore water diffusion rate still at 1 times 10 to the minus 8. So now this is 1 times 10 to the minus 9. So we'll see how this one behaves. Oh, let me load up my... Yeah, I mean, it might be a little less, but not particularly noticeable. So we'll see what happens with the particle mixing option. Well, if we're running out of, I'm kind of running out of steam on the toxics. I mean, we can play around with this, but I'm thinking we got a little bit of time. We can like pick up. We've got a number of different topics we can talk about. If you guys want, it's up to you. Yeah, I mean, it's not. I mean, the biggest thing you've got to decide really is how you split the HSPF constituents for water quality into equivalent bins for the kinetic model in EFTC. Okay. That if you're doing water quality modeling, and that can be anything from just, oh, I'm just going to do a few simple fractions to, you know, this one application, the guy wrote a whole big program to just, you know, do all the splits, and you know, it was just quite an involved process. So it really kind of whatever kind of fits the level of complexity of your project. If you're doing sediment transport alone, you have, you know, like sand, silt, and clay kind of compartments coming out of out of HSPF. It's not that difficult. I'll show you just generally the idea. Under the Boundary Conditions tab, we have the Import HSPF button. And in that, depending upon what your HSPF file you know, contains, you can, and of course, in what you're simulating, you have things that are available or not available based on what you're simulating. You can bring in different aspects, and then you can specify what column, you know, offsets, and, you know, be able to just import it pretty straightforward. When you're like doing suspended solids type of work, here you just tell it you know, which column the clays were in, and then what fraction your clays represent of or your, in this case we're calling it cohesive, but class 1, 2, and 3. Okay. And then likewise for silts, how you want to split the silts up and the sands up, and EE will do it all, and when you finish, you have all your time series for all your classes and everything all configured. And it gets, you know, like I said, it gets more complicated on the water quality, trying to split BOD and total phosphorus and stuff all into all the appropriate bins. And there's a method that does it here, but you know, we've used it and it works well, I think, but others like to be a lot more finesse on it. Yeah, there's you know, the view loadings. Let me just load up a model. Let me think. Let me load up a different model. This is Oklahoma 10 killer model. It's got a bunch of boundary conditions, and these are all HSPF inflows coming into this model. So we had these different subbasins coming in, and there's a lot of stuff going on. And so I say, what are the most significant boundary conditions? So you've got a tool here for analyzing existing models and your model if you want, but it's this view current boundary conditions. Loadings, and you can use this load table and just specify, this is boundaries. It could be a little bit cleaner as far as the user interface, but let's just say I want all the groups between 1 and 20 to be summarized. So I just enter my group and then go out and hit the view table, and it may take a little while, but it's going through and calculating the total mass loading for water, because that's what I currently have it assigned. But it'll also tell me any other constituent I'm simulating. And gives you that kind of big picture perspective of what's going on, what is actually contributing to the major loading in this system. So we'll let it crank through its thing, and then it'll pop up a table here in a bit. It's a 2-year simulation. Yeah, full-blown water quality. Meanwhile, back at the ranch, when you're running, I'm running interpreted mode right here, and when you're running that, it's always slower than running the release version. I don't know how exactly, I don't remember. We're getting close to the number of groups. Group 16. Maybe there's more than 20, so I guess, well, actually, there's 26 boundary groups right there. But I don't want to wait any longer, so this is just fine. Oh, I was going to say, wait a minute, where'd it go? Better put it on this screen. So summarizes your total mass. In this case, since it's water, it converts it to millions of cubic meters, and tells me that the dam released 1,475 million cubic meters during that 2-year period, and then the contribution of the different boundary conditions. I'm glad I caught these last two because they're the bigger ones. Yeah. So that's that tool, which is helpful. Let me see here. I'm just going to go back to the quicker ones, so they run quick. So kind of how to read the form. EE is trying to, scale things according to the view, but this particular, your model domain, but this particular model domain is so small relative to a real world system. It gets a little bit, you start running out of significant digits. So, but the way you read this is everything is converted to a common unit. So when you're looking at this table, in this case, we're looking at cohesives. So everything's been converted to metric tons. When we were looking at toxics, it's converted to grams or kilograms, I think. I have to look. Anyways, but the units are all consistent. So I can see how many metric tons I had at the beginning of this run.
Oh, okay.
So it's telling me I had 12 metric tons, and then at the end I had 11 metric tons, but this is just in the sediment bed. So the sediment bed lost a half a metric ton. However, that water, that metric ton, was gained by the suspended solids in the water column. So, you know, that's how you look at this, you know, this section of the mass balance report. So this is kind of looking at your beginning and ending snapshots for the sediment bed and the water column, and then beginning and ending at the end. And that's all it's doing. So in this case, they match exactly because your inflow and outflow from sediments are zero. But if these, and these may not be zero, so I mean your flow, this is the total metric tons of sediment coming in at your flow boundary or going out. If it's negative, it's going out. It's positive, it's coming into the system. So, but what you down here, this net balance, is it's looking at all the individual boundary conditions, how much is coming in and coming out, what we started with, what we ended up with, a sum of all your ins and outs, and then whatever is left is your mass balance error. Now the model should still have the model will produce a zero mass balance if everything's good in the code, but you may be drying out the reservoir because there's truly not a balance between the actual inflows and outflows relative to the volume of the reservoir. That's kind of a different problem. Yeah, well, you almost definitely will. On a reservoir, I mean, you got to remember that flow gauging is plus or minus 10%. I mean, with an ADCP, it's 5%. But if you're using an index gauge system, that could be worse. You know, and so if your flows are plus or minus 5, and you just you have measured data, and you say I'm going to use the measured data regardless, so that it's right, and you put it on a reservoir, you know the volume elevation relationship, you know your inflow, you know your outflow, you still have groundwater and evaporation and different issue, but it's very likely that you're either going to be filling up the reservoir too fast or you're going to be draining it too fast because of the imbalance. It's very, very common for these flows not to balance out right. So you have to usually post-process and either have makeup water, it's because of, you know, from groundwater, or you're saying that your flow measurements are incorrect. But if your volume elevation relationship is good and your inflows or outflows are measured and you want to straight up use them, you're going to have to do something else.
The makeup water, and then where you add it back to your inflows, or?
A lot of times, I mean, it's, you know, the makeup water. If you're draining the reservoir faster than what you have measured, you have insufficient inflow or too high of an outflow. So you have to make a decision. Is it really like, maybe is this really groundwater that I'm just not accounting for, or is this just imprecision in the measurement error? And that's a decision that the modeler will have to make, and then decide, okay, am I going to put this in as a groundwater source, or am I going to put this in, you know, just as the 10 killer decision, because the HSPF model drained the reservoir. So they had to have makeup water, and they bring it in at just a series of different tribs that they're calling local runoff. And to account for the mass balance difference or the water balance difference. And so, you know, that's how they made it up. But if you had, you know, a potentially significant groundwater source, then, you know, you might need to reconsider how you're putting that in. Maybe it is groundwater. Or you can have too high. It's either, again, still could be measurement error. Or maybe you need to account for evaporation because you're doing Lake Mead. And, you know, water's, you know, just leaving rapidly from your system. So it just, yeah, you got to use the engineering and scientific background to interpret what how to proceed.
So does EFDC have a tool to calculate what that difference is and then to know how it gets added back in?
I mean, indirectly, it does do it. Yeah, I mean, it'll calculate the volume lost through the volume elevation relationship tools that are in EFDC. I mean, if you come in here, and this one's going to be kind of a nonsensical thing with this flume, but
I know a C-qualm used to deal with that, and then you just add it back in through the distributed tributary.
it's similar, but you know, you might have to take an extra step to do it.
Okay.
So here, I've got a volume elevation relationship that's calculated from my bathymetry, and like I said, this is going to be with that crazy 1,000-foot or 1,000-meter deep hole, but you can use your area, volume, elevation relationship to generate the volume that you need for makeup,
Okay.
and then just put that back in through a distributed inflow.